So let's get started. So welcome. So thanks for those of you who braved the snow to make it here. So hopefully we can all make it home afterwards. I guess maybe around the time the lecture ends, the snow should, some maybe stop. So we'll see. Oh, so welcome. So thanks volume. For those of you who. Okay, so great. Shoot, now this is messed up. And so today we're going to be talking about so confidence intervals again, and in particular the T distribution. So we've talked about confidence intervals, so far when we had data drawn from a normal distribution and we knew the variance, and when we had data drawn from like a binomial distribution, which is kind of approximated by a normal distribution. And because it's binomial, we knew the variance again. T distribution kind of tells you what to do when you don't know the variance. So that'll be kind of the main point of the lecture today. We will kind of, again, this topic I think is a little bit kind of takes some while to wrap your head around. So we will kind of spend some time kind of like reviewing the main ideas again, not rushing through this to make sure that you have the right kind of understand this on like an intuitive level. I think once you get the right intuition for everything, then the actual techniques are fairly simple to apply, but you have to kind of understand what you're actually applying. So great. So if you have other things on the schedule, homework 6 has been posted. We mentioned that for the few of you here today, I've got some copies up front, and so in case you want to print out. And next lecture, we're going to talk about hypothesis testing, which is kind of the most biggest thing associated with statistics you see kind of actually outside the course. This is something we'll be very careful about and define kind of how to do a hypothesis test properly. Fortunately, there's a lot of misuse of hypothesis tests or not quite understanding what this means, and so we'll talk about some versions of this, and we'll again take our time in going through hypothesis testing. But we're pretty close to the end of the semester. A couple people started asking me about the final. Kind of, if you haven't seen, the university gives us the date of the final. You shouldn't have conflicts if you're not also in another class at the same time, which I think is all except maybe one person in here. And so there's a practice exam and solutions posted there to give you a sense of it. I haven't looked at the practice exam in a while, but I assume that'll be pretty close. It'll be in the classroom on paper, so a bit different than what we've done earlier, but it should, you should, if you're doing well and keeping up, it should be something that in the time period you should be able to kind of solve all the questions, I think. Kind of like we don't want time to be an issue in completing the final. And there'll be some sort of kind of sheets that you can bring in. So I won't make you memorize everything. And I'll specify that as it gets a little bit closer. We're still figuring out the details of that. So great. Let's get into the lecture. All right. So let's back up a little bit with the main premise that we're talking about. Statistics. Okay, and what do we mean by this? It means that we have a a sample, and we'll think of this as x1 up to xn, and these are drawn IID from some distribution parameterized by some parametric distribution. Continuous distribution, that means you can define it by just a few simple parameters, maybe one, and theta is going to generically be this parameter. Okay, and we would like to estimate, we would like to try and understand something about the distribution it's drawn from, right? And how do we understand that distribution? We'd like to say something about that parameter, so theta. So the question is, what can we say? And then so probabilistically, okay, because we're gonna use probability. So about so f of theta, and so really what we mean is about theta, right? So there's some parameter we're trying to estimate. Sometimes there are multiple parameters we're trying to estimate. You can sometimes do them jointly. This is more complicated. In this class, we'll just think about one parameter. We'll estimate one parameter at a time, I guess. We'll talk a little bit in this lecture if there are kind of two parameters you want to estimate, but we'll do one and then the other. And we'll mainly talk about how do we understand just one parameter. Okay, so the first thing we talked about was a statistic, which we'll call, so the theta hat, which will be some function of x1, x2, up to xn. And if you remember, these are so random variables. X1 through xn are random variables. We haven't actually touched the data yet. We're going to think about what happens when this is actually data, but we're reasoning about it. So when we look at data, we know how much, what to trust, how much to trust the data, right? Or what we can say about the actual data we get. Okay, so we're going to create some, some statistic. And usually if you put a hat on top here, right? So this hat means that this is going to be an estimator of theta. So theta is a real value, right? So this is theta is a constant. It's something that's true. There's some unknown parameter theta, but it is a fixed value. Whereas theta hat is also going to be whereas this one is going to be a random variable. So it has a probability distribution. And then we're going to think about two things we can say about the probability distribution. One is the bias of theta, which is going to be the expected value of theta minus of theta hat, right? It's a probability distribution, so we can take its expected value, and then we can subtract off the true value of theta, right? If this is 0, it's going to be unbiased. We want to say if we just look at this one value, do we think on average is this going to be the right value? Okay, but it might not be close to the right value. So how close is this actually to the right value? The second thing we've been talking about the last few lectures is a confidence interval. Okay, and this will be an interval L. We'll call it Ln, and this will kind of be often be a function of theta n. You can think of it as this. And a right value. These are a function of theta n. This is what we used before. And it should have the property that the probability that the true value of theta, right, is in this range, Ln up to Rn, is going to be equals to 1 minus alpha. Okay, so this would then be a a 1 minus alpha, I guess, times 100%, so confidence interval. All right, and what's important to realize, again, theta is this, right, is this constant value, right? So theta is the value that is constant, and the probabilistic part is the ln and the rn. Both of those, again, have probability distributions, and so the probability is based on the ln and the rn, which again are these random variables. They have distributions. We've only dealt with symmetric distributions so far here, and then ln and rn kind of have, you can look at a probability of kind of, being too far to the left or too far to the right. It's going to be symmetric, so we just need to worry about one. The other one is like the symmetric version of that. But there are other cases where it's not symmetric and you have to kind of worry about these jointly, and that can be more so complicated. Okay, so a picture way of thinking about this is that there's going to be a real values, right? And there's a true value of, theta describing the underlying, distribution, okay? And then we're going to draw some samples from this distribution. We don't know what this distribution is, right? But there might be some, distribution here, f of theta, okay? And we're going to draw some samples, right, which are drawn from this sort of kind of distribution, x1, x2, x3, x4, x5, okay? And I'm kind of drawing them abstractly here. And they're all drawn from this distribution, right? So these are all x1 up through xn are drawn from this distribution. But there's also going to be a often an xn bar, which is going to be I equals 1 to n, the average of these, right? And so this will be kind of a tighter distribution. This will be f of xn bar. And so that should have the same mean by the central limit theorem, right? So this is also the expected value of xn bar is the same as theta, which means it's going to be an unbiased estimator, but it's still going to be a distribution, right? So if I actually realize the sample from this, it's going to be somewhere here. It might not be exactly theta. Okay, all of these have been uppercase values. Okay, but what actually happens is that at some point we're actually going to look at some real data. So down here below is real data, and so this is where you actually make some observations. And so we don't know what theta is. All we see are these actual values, lowercase x1, right? Lowercase x2, x3, x4, x5, right? And I'd like to say, well, I'd like to estimate the parameter, the mean value of this distribution, right? So I'd like to estimate, kind of understand what is the distribution these came from. One way to estimate theta is just to look at just one of these values, right? I could look at just x1 and say, that's an okay guess for theta. It's an unbiased estimator of theta. I picked the first one. But what's better is to kind of take the average of all of these, right? All of these, so I can take the average of all of these. This will be x5 bar, right? This is the average of all of them, and that's a lowercase x. And this is some estimator of theta. I don't know where theta is, but I know in expectation that knowing the process, X1 would have in expectation given me the right answer. X5 bar, the average of them, also in expectation gives me the right answer, but it might not be exactly the right answer. All right, so I know, well, then I can say, well, the probability distribution of where theta is, I know that there was this purple distribution around theta, and I said the probability of where X5 bar was drawn from is from that purple distribution. So if I wanted to look at the difference to where I can draw these values in this so distribution, this length, this margin, and I say, if I know this length is, so much, let's say, so this would like be the, so let's, so call this length. I know that from this distribution that the area under the tail outside this distribution is maybe like, so 5%. Okay. So I want to say, well, now I can say that there's like a symmetric property that a 5% chance that this, that the distance, so I can say that there's a, there's a 5% chance so distance from theta to X5 bar is greater than length, right? So this length was equal to something like this Z alpha over 2 times the square root of sigma, or I guess, so sigma over, so like square root n. That's one way of getting it. If we knew this was from a normal distribution, right, then we can set the length equal to this. And then we can take that same distance and put it around. So because it's just the distance from theta to X5 bar or Xn bar, then I can do the same thing and say, well, if I look at X5 bar, I can put the same distance around X5 bar and say the probability that theta falls in here is also 95%, right? So also theta is in X5 bar plus or minus, so this length with 0.95, so probability. Okay, because I'm measuring distance and that's so symmetric, I can actually put it on the observation and say the true parameter is in there with this probability, assuming these are drawn from normal distributions with, so this one tells me it's drawn from a normal distribution. This tells me that the variance of the normal distribution was sigma squared, and n, is the number of things I'm averaging to get this estimate. Okay, so when you actually get data, you're putting a confidence interval around the true observation you get, and you're saying the probability that the true unknown parameter theta falls so close to that. Okay, but you start from the original distribution, which we can analyze analytically using probability, and then when we apply it to data, we can say, okay, we think the true value is in here, right? We went through this example on Thursday last week with the polling example with the binomial random variables. That theta parameter was the probability that, say, the rate people were voting for, like, Mike Lear or so Spencer Cox or someone in the election. We're trying to do that from an estimate and get confidence intervals where, say, that was around 3%. We needed around 1,000 people in the poll. Yes. Okay. So this is kind of what we've done up to this point. this kind of help as a refresher to see this again a little bit? So, okay, great. So what I want to talk today about is what if x1 through xn are drawn from a normal distribution, mu sigma squared, and we do not know sigma squared, right? So what we've done so far, we've said, we assumed we knew what sigma squared was, and then by the central limit theorem, we said, well, sigma squared, or the variance of the xn bar, right, our sample average, that was sigma squared divided by n, and then we could compute the confidence interval that way by mapping everything onto the, what we know about the normal distribution. Well, what should we do if we don't know sigma squared? We say we're still going to assume that our data is drawn from a normal distribution, but kind of, by this central limit theorem, we know if we're still gonna do something like an average, and we know things are gonna kind of approach the normal distribution if we take enough samples anyways. So this could really be samples from anything, where we're just trying to compute the mean of the distribution. If it doesn't look too crazy far from a normal distribution, it will be converging towards it pretty fast. Even the Bernoulli distribution, if we drew samples from that, we saw after about 100 samples, it's going to be so pretty close, right? So we can often get pretty close to a normal distribution of the average. So now we don't even need to know very much about it, but for now we're going to explicitly assume that it comes from a normal, that our data is from a normal distribution like snowfall or rain or time estimates of some event that takes some time. These are pretty common to assume from some normal distribution, but we don't know what the true variance is. Okay, so what should we do? All right. Yep. Yeah, great. So perfect, right? So instead, we want to kind of estimate the variance first. We can estimate the variance with the sample variance, right? And if you remember what this is, it's Sn. We use Sn, and this was 1 over n minus 1. I equals 1 to n of the xi minus the xn bar squared, right? So another estimator of the variance would have been, right? So what we could have also done 1 over n, I equals 1 to n, xi minus the true expected value of xi squared, right? So this would be a closer definition of the variance, right? Where we're sampling these random variables and looking at their expected square deviations from the mean, but we didn't know the mean. So instead, we used a sample estimate of the mean instead, and it turned out that meant that we needed to normalize by 1 over n minus 1 instead of, so n. So what we're going to kind of do here is we're going to use the sample variance, which uses an estimation of the mean, to get a confidence interval on the mean. It's kind of a chicken and egg problem here. And we'll we'll kind of skip over that, and I'll give you kind of like a distribution where you can look up something in a table. Okay, but yeah, we're going to use the sample variance to estimate this variance. And reminder, to do this, we need to divide by n minus 1 instead of by n. Okay, and this should point to you that, okay, we need to be careful when we're combining these estimators. We need to do this because we didn't know the true mean. So we're trying to kind of figure out how to do this. So now we want to get an estimator for the confidence interval. Okay, so before, if we know, so the true variance, then we could say that the confidence interval was going to be xn bar plus or minus z alpha over 2 times sigma over so like square root n, right? So if we knew the variance, it was going to be this. So we're going to somehow need to do something like this for the confidence interval. This is this plus or minus confusing. This is instead of writing the left hand and the right hand side, but we need to kind of offset it by this much, okay? And we want to do that, but we can't use sigma because we don't know sigma, and that's similar because we didn't know the true value of the mean here. We had to estimate this instead. Okay, so we're going to plug in something. So instead, we're going to say, well, the confidence interval in this case is xn bar plus or minus something like z alpha over 2, but I'm going to fix this later. Sn, the square root of Sn divided by so square root n. Okay, so we're going to do this, but instead of there's kind of this I wanted to. All right, and there's kind of this thing where we're replacing the sigma with the square root of Sn, which is the sample estimate of the variance. All right, but like with the sample estimate of the variance, we need to change something slightly here, right? Instead of using 1 over n, we use 1 over n minus 1. We somehow need to correct that we're not using the right value, all right? And so where we're going to correct it is in this guy here, the z alpha over 2. This was for a normal random variable, but it's not quite a normal random variable because there's also this estimation, which is a random variable, which creates more randomness in the process of what the true distribution of xn, so xn bar, right? If you look back at this picture, we had that purple true distribution of xn bar, which we could use to get the distance. How far did we want to go? And then we could translate that onto our actual data. But if we no longer exactly have the distribution of xn bar because we don't know what the right variance was anymore. We're guessing on the variance. And so we need to factor in that guess into that distribution. And that kind of gets you can imagine it's a little bit complicated, but it shouldn't be too different either. It should look kind of like that distribution, but be slightly different, okay? And so the answer is that we're going to replace this with instead the z with t. Okay, I just put a t in there and I've solved the problem. All right, so I just need a different function, a table there that I need to look up in a different table if I use the sample variance instead. Okay, and people have worked this out. So the story of this, so this will be called, this is from, students, so, so, so T dis, so T distribution. All right. And so this is kind of a distribution, which is, the kind of where we evaluate the quantiles at alpha over 2. So it's what you use in the place when you use the sample variance. So instead of the variance. Yeah. So it's okay. So has anyone, have they heard of students' T distribution before? Yeah. So do you know who student is? Yeah. So the story about this is this was published in a journal in like 1908. So in 1908. So it was published under the name student, right? And so there was someone who worked at a company. This sometimes happens today, and wanted to publish this result because they thought it was really cool. It'd be useful for statisticians, but his company wasn't sure if they wanted him to publish it, so he sent it in not under his real name. All right, so the guy's name was actually William Gossett. I spelled that correctly. So 2 T's. So the company he worked for was Guinness Brewery, beer making, back in, over 100 years ago. It was a science, as I think it actually is so still today. You have to test stuff, get the proportions right, see stuff, and wanted to figure out how much to be confident in various parameters based on some tests. And he worked out this calculation, this distribution, and said, look, this is the right way to do it. You can't use the real variance, you have to use the sample variance instead, and that changes this distribution slightly. All right, and then there was a couple things that weren't exactly right about this, and this was fixed by like Ronald Fisher, who we'll talk about again. So on Thursday actually, and so he tweaked a couple things in this, but it was William Gossett who had the main idea here. So this seems like a pretty simple, fix here. Right, so to get the confidence interval, so this is the let's see, the 1 minus alpha. So like if it's alpha is 0.5, that's 95%, or 1 minus alpha times 100. So confidence. So interval for xi from iid, for the mean, when you're drawn from a normal distribution and sigma squared is known. Okay, so if sigma squared is unknown, you use a T distribution instead of, and the sample standard deviation instead of the known standard deviation and the Z distribution, or kind of this version of the normalized normal distribution. All right, so let's look a little bit at what is the T distribution. So before I say this, before we look at this in R, the T, so often use like the T distribution. All right, so we usually say that this will be written, so it's usually written with called with the lowercase t, and the random variable would be Tn, which is drawn from a T distribution with n minus 1. Okay, there's one parameter because we only consider kind of the one that has mean 0, and the standard deviation looks kind of like, so 1. Well, we don't know this what the standard deviation is, right? But it's kind of been normalized properly. Like, so it's kind of similar. So it's going to be, so this is going to be so similar to an x from a normal distribution with mean 1 and mean 0 and so variance 1. But this only has one kind of parameter here. It's written as n minus 1, and this is called the degrees of freedom. Okay, and this is the number of random variables we have, but we're kind of using this to estimate the sample mean. And if you have the sample mean, that kind of, you have this relationship between all the variables encapsulating that. So it kind of takes off 1 degree freedom. So a similar way, like we divided through by the n minus 1 for the sample standard deviation instead of dividing by n, there's a similar reason we use n minus 1 here instead. It turns out to be the kind of the key parameter. And so, but you don't assume, like, you don't parameterize it by the mean or the variance or anything like that. So, and so as n gets large, as n gets large, it actually approaches as n goes to as n goes to infinity, it actually approaches like the standard normal distribution, right? So for small n, it's going to look a little different. For big n's, this is pretty much going to look the same. Okay, and the reason to understand that is if you have large n, your sample estimate of the variance is actually going to be quite good. So the difference between the true variance and the sample estimate is going to be pretty small. And then this will, and then the confidence interval bound you're going to get is you're going to basically use the same parameter. Z alpha over 2 is going to work about the same as T alpha over 2. Okay, so this is a distribution with one parameter. And so it's going to look pretty much similar to the normal distribution. Let's look at an example here in R. Okay, so I'm gonna, let's see. All right, so first let's set alpha equals 0.5 and do n equals 10, right? And so now I want to, right, so to evaluate it, right, I'm gonna say the quantile function. Remember, we used the quantile, the normal distribution before, and we did it 1 minus 0.5 times alpha because we only want the tail on one side. This will give us the value of the upper tail. But before we had to put in maybe the 0, 1, but now we put in n, this number of, it depends on n. As n gets bigger, it approaches the normal. As n is smaller, it's going to look something different. So it passes in the value we approximate at, that's 97.5. So when the quantile function reaches almost the top, how far from 0 should that get, right? And so it gives us a value of 2.26. This is if we have 10 samples we're averaging over. If I instead had did the normal distribution of 1 minus 0.5 times alpha, say for 0, 1, right? This was, 1.95, right? Or about 1.96. So this is larger. We're gonna have to push the confidence interval distance further out to ensure we capture the right parameter with 95%, chance. Okay, but if I were to increase the degrees of freedom, let's say to say 99, I had 100 samples instead. Well, then this is looking pretty close. It's 1.98. right? And if I put in, if I have 1,000 samples, 1.962, okay, it's into the fourth digit of precision at this point. Okay. So again, if you have 1,000 samples, everything you're gonna estimates are you can feel pretty good about those estimates. So okay. Let's try, just to see how to plot this. Let's see. So if I plot this function, what did I do wrong here? Let's see. So if I do this for, what did I do wrong? The distribution of the T distribution needs degree of freedom. Let's say 9 again. Okay. And I applied this in red. This plot, I think if I zoom out, the plot will look better. Okay. So this is the T distribution. It looks a lot like the normal distribution, right? Centered at 0, like the standard normal distribution, about distance 2 is about 95, 95% of the mass is out about a distance 2 in each direction. Okay, if I plot let's plot the normal distribution on top of here. Okay, so norm from, the normal distribution 0, 1, right? This should, okay, so you can see the normal distribution looks very, very similar, right? So you can see the normal distribution up there in blue. The difference, so what is the difference? Kind of the interesting thing is, how are they different, right? The red one, which is the T distribution, is a bit wider in the tails, right? So there's more probability further out from the mean. And there's, which means I have to compensate close to the mean, right? There's less likely to hit it. I'm more likely to be in the tails. And that shows up actually in the interesting areas about kind of 2 to 3, so like 2 to 3 standard deviations out. Okay, right, so 2 to 3 standard deviations, this is when I'm about 95% confident. See a little difference. If I'm 90, I have to go out to about here to get 99% confidence interval. And there you actually see the differences a bit more. So it's actually different in the interesting parts of the distribution. It's not too different. It's about the same. If you use the normal distribution, you're not going to be too far off. But it's not quite right. And this is only if I only average, so 10 samples, right? If instead I wanted to draw, let's draw this instead with purple. Make sure I add this on. And then let's draw it with, we have 100 samples instead, right? So I changed the 9 to a 99, right? And okay, it's up there. Can you see it? It's pretty hard to see, right? Because it's right on top of the blue curve. Actually, the blue curve basically just, so turned purple. Okay, so the blue curve turned purple. It's a little bit higher than the blue curve in the tails. There's still a little bit more tails, but it's pretty close, right? So there's a slight difference here, but not too much. And so that's reflected. Yeah, remember if we had 99, that instead of 1.96, we have 1.98 as the value that we're spreading out here, right? So it's really pretty small values differences as you have 100 things you're averaging. kind of in the field of like statistics, especially in like 1908, it was much more common to have the case when there were only 10 samples. Nowadays, there are definitely cases, some medical trials where you only have on the order of 10 samples. But in machine learning, you often have hundreds of thousands, millions of samples to evaluate. And there the difference is quite small. But still, if you're dealing with small data set sizes, this actually makes a difference. Yeah. Okay. Any other questions on the plots, things you want to see? Yeah. You can't, right? You just have to accept it. You have to have less confidence. And the interval is wider of where the true parameter might be. And you should report that, right? You shouldn't overconfidently report so what the range, the interval you think the true parameter is, right? Whether that's kind of a rate of infection of COVID or the population, so the percentage in, if you're trying to estimate, what the snowfall was going to be yesterday, right? They said, well, it might be really bad yesterday, and the university decided to, we should move classes online, and said it might not be so bad today, and then it was a little worse today, and we kept classes in person. But so there was some confidence in this estimate, and if you don't know the variance, then you shouldn't kind of report it as if you did know the variance. You should report it with more uncertainty, right? So it's important to kind of, to measure. I mean, there's a question of saying that when you're trying to truthfully report like an estimate of, something from data, most people would rather you report it with more confidence, right? But if you say I don't have a lot of confidence about something, then it's hard to evaluate how that's better, but you can do it, right? You can look at a bunch of predictions over time and say, okay, when you said your estimate should fall in there like 95% of the time, you expect out of 20 estimates you make, one of them should be wrong, right? So one thing, one interesting place to look at this is, so like the estimates of like elections. So if you look at like 538, it tries to look at a bunch of polls and aggregate data and make predictions about who's going to win elections. And it puts some amount of confidence in these predictions. It's very good about actually reporting these values. And there were a few races, it actually, I think it does so quite well, and especially in reporting its confidence. And if you look at the races, there are some races that said we're 99% confident in this prediction. And there were 100 races like that. And there was one where they got wrong, right? And that was about as expected, right? So you kind of need to look at this. You shouldn't like give more confidence than you actually have. Now, there's a lot of pushback about 538's predictions, mostly because people don't quite grasp what they're presenting about the confidence. They're saying, we think, with the election between Biden and Trump, I think they said, well, we expect like Biden's going to win, their confidence, they're saying, we think Biden's going to win like, was it like 75% of the time, based on their results the night before the election, said, we're predicting Biden, but we'll be wrong 25% of the time, right? And they had predicted Clinton instead of Trump earlier, but they said we only think Clinton will win 2/3 of the time in 2016. And they were wrong that time, but most other places predicted the same thing, but with higher confidence. And so they got flack for predicting that kind of incorrectly, but they had the least confidence. So maybe that's, they claimed it as they did better than everyone else who predicted the same thing, but with higher confidence, and they were less wrong than everyone else. Yeah. Yeah, so it's kind of tricky because you can't yeah, so each election is like its own so perfect snowflake or something, right? That it's not exactly the same as as like another election. The way they try to do it is they have the presidential elections are tough because there are not a lot of them, that and polling and the way polling is done and is changed only a few times. And I mean, there's only been about like maybe 10 elections in the modern era of so polling, so it's not a lot of data. But like the congressional races, they're like every 2 years there are like 300, 3 to 400 of those, right? And so they have, or is it 400 some? And so they have a lot more data on those. They can say we're going to use the same model and we're going to generate confidence intervals the same way, and then you can kind of see how well they did. And they try and present that after every election. Yeah. 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 So the question is, how do you, like, if you don't have a lot of data, you want a high, and I see there's a good question on Zoom, I'll get to next. If you don't have a lot of data, you want to somehow you would like to have a narrow window of prediction, right? So you don't have a lot of uncertainty, but also a high confidence. What's the right thing to do? So I would say the right thing to do is not to lie and overstate your confidence. You should. There's always a choice of what do you choose for like the alpha value, right? Do you want 95% confidence or 99% confidence or 90% or 70% confidence? Yeah, so that's hard to say, right? You could choose either. You can actually present multiple confidence windows, right? For the same data, it gives you multiple confidence windows at different levels of alpha. What's the right thing to do? Using alpha at 5% is pretty standard. 95%, 1 out of 20 chance of being wrong seems reasonable. For some cases, you really don't want to be wrong, right? And so you go to 99% or 99.9% if it's like really important. If they do stuff on like the space shuttle, like at NASA, there are lots of things that can go wrong, and they put a confidence interval around all these things. What's the probability that something happens that could lead to the space shuttle exploding? And because they have lots of different things that can happen, they put the confidence extremely high. So alpha might be 1/1000th of 1%. Okay, but then they have a lot of these events, and they use something called like the union bound. Say, well, if any one of those things go wrong, the space shuttle might blow up. So I might have 1,000 things that can go wrong, and so I want maybe a total of 1% chance that something goes wrong. That means that there are 1,000 things at 1/1000th of a percent that can go wrong, and so that's where they put their confidence bounds. So sometimes you want much higher confidence, and you have to then maybe that tells you I need to collect more data in order to get that level of confidence or more precision into the manufacturing process, right? So you can use that to guide, do I have enough data? Right. So that kind of answers your question, but like this is what we study the probability of these things, because this is how much confidence you should have. You can't like add confidence or get less uncertainty into it after you've collected the data, right? Unless you go and collect more data, right? So, okay, so there's a question on Zoom. I've been, two people told me to think, would this apply? A ChatGPT question. Oh no. Would this apply to a language model such as ChatGPT with high confidence in an incorrect response? Yeah, okay. Okay. Finally, the ChatGPT question, right? So ChatGPT, if you don't know, is this large language model based, so chatbot that that can answer stuff using some natural language, and it does extremely well at following the patterns of natural language. And you can type in a question, it will respond with a natural language response, extremely well at that, and it will respond with a single correct answer. Right. So the analogy with ChatGPT is that it is giving you the estimator it has. Okay. So it is, if you think about, let's go back to, right. So with, if you go back to our picture here, right. So you would think of with the data, remember the actual data is on the bottom. We don't know where theta is. We have an estimator, X5 bar, which is, say, our guess of where the data is. And we have the band of, we say, well, we think that, or not the data, the parameter is. And we have a band, we say 95% of the time we think the parameter is within this green region, right? That is, right, in this green region here, we think 95% of the time it falls in. What ChatGPT does is it always answers what it thinks is the most likely solution. It always will return kind of this one estimator, and it says that's the answer. So it has, so it has lots of data, right? It's trained on kind of like the whole internet, right? So it has lots and lots of data. Why isn't it super confident? Why shouldn't it be super confident about it? The question is, it's not estimating just one parameter here. It's trying to estimate in this enormous parameter space, right? The number of parameters in the model that ChatGPT uses, I don't know, is it billions or trillions, right? It's like, we're not just estimating one thing, we're estimating trillions of things jointly. It doesn't need to get all of them exactly right, is not the right thing to think about, but it's trying to estimate lots of things, and it gets many things of those right. That's why it looks like natural language. But it doesn't always get all of them right? Sometimes it gets part of the answer right and part of it wrong, but it presents it all as being correct, right? So it would, if you could, how to report confidence and confidence intervals accurately within these neural networks, which are super complicated, is a really active research area. And for simple neural networks, we're starting to be able to understand this. For things like ChatGPT, which are 1 billion times bigger than these things that we know how to deal with, we don't have a good grasp of how to do that yet. I'm hopeful we as computer scientists and kind of statisticians will figure out how to do that over the next 5 to 10 years. But at this point, that's a big weakness in this, and I think it's a really important direction that I hope to see some progress in. Yeah. Oh, okay. Yeah. So great. Yeah. Yeah. Okay. So in order to train ChatGPT, they have part of the process, and a lot of large language models do not inherently use people who train it in various ways to build them. But one thing that OpenAI did that allowed it to make a lot of progress in the last year or two is in addition to training this thing that generically on just the language, they hired a huge number of testers mostly in like the developing world or the global South, and ask them yes or no, did it do correct on this task, right? And use that to train it. Is that helping evaluate the confidence intervals? That's mostly not what they did. That would be a great thing to try and do, to try and understand the confidence intervals in the answer. Most of what they were doing was trying to optimize the actual parameters inside the model. They were using that more to get a better and better estimate of like the X5 bar, but think there are billions of these, hundreds of billions of these parameters, and they're getting a better estimate of those by asking specific questions for subsets of those at a time effectively. And they're getting better estimates of those by kind of, the statistics do not need to be the mean. Statistic could be kind of any process here. And they have more complicated statistics to get estimators for the appropriate parameters. And they're kind of using that to tune those. I don't really know, it's like proprietary, but I don't think they were using it to tune the confidence. That's not consistent with the reports coming out of this that we've been. Yeah. 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 Okay. So another comment was the StarCraft AI, or I'm guessing similar with like Deep Blue playing chess and so forth. These are games that can play against themselves in a particular closed environment and system, and they could estimate the confidence of winning at different states in the game as they were doing this, and they could have been in very similar states so in the past and played out those games and had a sense of how many times they won or lost based on those states, right? And so in that way, they actually had they were, yeah. How would that relate to this? So it would say things. So like with winning or losing a game, right? There's another thing going on here where there's some sort of like threshold in the space, right? And you win if you're on one side and you lose if you're on the other, right? The right analogy that we've seen deeper in classes, like with the polling in politics, you win a race if you get over 50% of the vote. And so you want to predict the probability that you win the race, right? Or your probability that you are going to win the game. And so you can kind of, and so in the simple setting here, it means that you actually have more than, you're past this on one side of this, you win if you're on one side of the threshold, right? And so you want to say, what's the probability that you're on one side? And that's a little bit different than the confidence interval, I guess. That's kind of, you're estimating the probability distribution of ending up in a winning or a losing state based on the data. But you can kind of read it off here based on the confidence interval of like what fraction of the data, like you could tune the confidence interval to be really narrow and maybe say the 75% confidence interval is completely on the win side. And then you'd say, well, then there's only a 25% chance I lose, right? So that's how you can more directly get this. What I've lost is there's a two-sided interval, so I only want to do this on one side. So I don't need to use like Z alpha over 2. I can use Z alpha because I only need a one-sided kind of Z value here. But that's how you would apply the techniques we've learned here in order to kind of estimate the win-loss probability in this way. Yeah, so these are great things. There's a lot of other things you can do with these statistics, and this class is kind of touching the surface on this, but it's good to think about how these relate to kind of situations, outside in the world. All right. So I'd kind of I was hoping we would have a bit more discussion today, so this has been fine. Any other questions or a couple more things I want to say about using t-distribution and such? So, okay. So great. So let me, I want to now, so compare, let's try that again. Compare the, so the distribution, so if we look at the, let's see, x n bar plus or minus t alpha over 2 times sigma over square root n, right? And so this will be the half length of the margin. Okay, this is if we use the so the normal distribution. We can also compare xn bar plus or minus, oh, I wrote the wrong thing. This should be z alpha. If I wrote t alpha over 2 Sn square root divided by square root n. This is with the t distribution. Okay, how do these compare to each other? Okay, right, again, the t, so half length. So which one of these is larger? So is kind of the size of the confidence interval going to be bigger for the using the t distribution, or is it going to be smaller? Yeah, so that non-confident answer was actually correct. So so let me state this precisely. The t half, so length, is so bigger than the z, so half length, so probably. Okay, it's not always bigger. It's probably going to be bigger. It's usually going to be bigger. But the thing is, the t half length, right, also has in it this sample. It's got in it the sample estimate of the variance. Okay, and so we might have so maybe Sn, right, is too small, right? I might, because I'm estimating the variance, maybe my estimate, because of the randomness in the process, it's a random variable, it might be smaller than sigma, right? There's some chance it's smaller. When it's smaller, then the half length of the t distribution will be actually smaller, and you'll be more confident. So you might be more confident than you should be, but that's, that is played out. The chance of that is built in to that alpha parameter. Okay, to counteract that is why that we know that t alpha over 2 is greater than z alpha over 2. So we know that t alpha over 2 is greater than the z alpha over 2, and that is explicitly to counteract the fact that the Sn square root of Sn might accidentally be smaller than the true value of sigma. So to counteract that, you need to make the T alpha n larger. And so that goes into the, the probability that it's way smaller and the T alpha n wasn't big enough, that goes into the alpha term. Yeah. Yeah, the sample variance is an estimate of, so the uses an estimate of the mean inside of it too, right? So that could also go wrong, right? So I believe that the first version of the T distribution, so from Gossett, did not take that into account. Did not take into account that you were also estimating the mean and the sample variance, and then this was later fixed by Fisher, and that's what we use today. Yeah. But that, we saw these are already pretty close to the normal distribution. And so that difference is even smaller deviation. And so it was, was even less of a difference. But you should also pay attention to that. Yeah. Yeah, so there's a lot. This is a good question. Like, there's a lot going on here, right? Sn might actually be larger than sigma squared, right? So then the confidence interval is larger than it actually needs to be, right? And this is kind of complicated. I haven't tried to write down the whole distribution of the bounds on the confidence interval, the Ln and so the Rn. All we've tried to calculate, right, is we try to set things up so that the ln is less than or equal to, well, let's say, so mu is less than or equal to, so Rn equals 1 minus alpha, for ln equals xn bar minus t alpha over 2, Sn over, so square root n. This is the only thing that we're claiming, right? So this is all we're claiming, that the probability that mu actually falls within those bounds is 1 minus alpha. And that's trying to account for all of these weird things that can go wrong, right? Our mean estimate inside the sample variance could be wrong, right? The sample variance might be too big or it might be too small. And we've used the T alpha over 2 to correct for that. And that all gets thrown into kind of this value T alpha over 2. Okay, and so we're just doing this. We're not actually, I haven't tried to put a confidence bound on the estimation of the true value for like that ln is trying to represent, right? It's a random variable, and I just use it within this probabilistic statement, right? So as you can imagine, statistics can be like a rabbit hole, and you can go deeper and deeper into trying to understand, what the variation actually is here. But at some point, it's not as useful. Even this statement, it took all of us, I think, a while to kind of really understand what this is saying. And if you starts putting these statements about the lower bound or the upper bound of the confidence interval, fewer and fewer people will actually understand it and interpret it correctly. So I would say a good piece of advice is trying to balance the complexity of what you're telling people to the usefulness of it. And the confidence interval seems to be kind of a useful thing that hopefully you all understand going forward, and you can work with this. You can go deeper into these things, and some people will understand those, but they probably will need to be kind of specially trained. And so I biostatistician friends who work up in the hospital, and they worry about a lot of these things, right? And they need those for nuanced points about how some treatment is working. But so that's meant for a specialized audience, right? And that's why we have like the FDA to approve stuff instead of just like, let's see what the public thinks, right? For reasons that some of this gets kind of complicated and, so nuanced. Yeah, but there's it's interesting kind of there's a lot going on in here, but we're just making this claim. Okay. Maybe you have time for one sample example problem. So we did this example before where we had n equals 40. So snow stations. Okay, and we took these sample estimates, and we have that xn bar where n equals 40. This came out as 620 inches. And we said, so before that, we claimed that sigma squared, the variance, was going to be 36 inches. Okay, and then afterwards we said, standard deviation of 6 inches on these measurements, that's probably not right. So maybe this claim was wrong, right? What we didn't actually know what the true what the real variance was. So how would we get confidence intervals on the actual like snowpack in this setting? We'd like to get a 95 percent confidence interval. Okay, so how would we go about doing this? Now we're going to claim that based on the measurements, that Sn squared, or Sn, let's say this came out as 34 inches. Okay, so we're going to estimate this. This was equal to 1 over n minus 1, I equals 1 to n of xi minus xn bar squared, right? And remember that this was 620. Okay, and that should be inches squared, I guess. Okay. Okay, so how do we do this? We're going to say the confidence interval is xn bar plus or minus t 0.025 times square root of Sn divided by square root of 40, right? This is this term. This term, well, we know that, let's see, let me look back on R. We said let's plug this in here. Okay, let's say we have 40 measurements, and we want the point, this alpha is still 0.5. So we're going to say that, so we have 2.02. Okay, so we're going to say that T 0.025 is 2.02. Okay, and so then we're going to say this is equal to plus or minus 620 plus or minus 2.02 times square root of 34 divided by square root of 40. Okay, let's go back into R. Okay, so we're going to say 2.02 times square root of 34 divided by square root of 40. Okay, and we're going to get 1.86. So we're going to get, this will be 620 plus or minus 1.86. I think that's still probably too small, but now we actually measured the sample variance. Maybe that year there was a very, like uniform, so snowpack across these things. And the standard deviation was a little bit less than, sample standard deviation, a little bit less than 6 inches. So we might as well trust it, right? That seems, if it really was pretty uniform across them, then I'd feel a little bit more confident in this, than we did before. Yeah. Yes. Great. Thank you for correcting me. Yes, this should be 39. Okay, still 2.022. Okay, great. So my calculations on the other sides here still pretty much work. All right, awesome. Right. Again, the small difference between n end up giving pretty small, so changes in the distribution. So great. So let's stop there, and then we can take more questions about ChatGPT after the lecture, and we'll start hypothesis testing on Thursday, and I'll start from the beginning of his